Welcome back. We've been talking about quantization of signals, and we're going to talk about quantization of filters soon. But first, let's talk a little bit more about digital filters. We've introduced the idea of a system function or a transfer function, and the z-transform has enabled us to get some intuitive idea of what's going to happen with a filter by the location of the poles and zeros. But we're going to spend a little bit more time diving into that, and when we're done, we'll have some ideas about how to design filters with specific characteristics. The first thing I want to talk about is linear phase. So the phase response of a filter is given as follows. So this is read as the angle or the argument or the phase of a filter h of e to the j omega. So we often, this phase function would be a potentially nonlinear function of omega, and we might give that as theta function of omega. So for example, if we have h e to the j omega is equal to the magnitude of e to the j omega, or h of e to the j omega, times this phase term, that phase term there is what we're talking about. So if h of e to the j omega is symmetric about 0, then it's real. This is a property of the DTFT, and in this case, the angle or the argument of h of e to the j omega is going to be 0. It could also be pi, right? And there are two schools of thought here. And I'll explain that a little bit more as we go along, but if h of e to the j omega is negative, it can still be real. But once it's negative, in order to do this magnitude phase factorization, this negative portion has to show up someplace, and it shows up in the phase as a phase of pi. So as a function of pi, this could be either have a phase of 0, as a function of omega, it could have a phase of 0 or a phase of pi. Well, if a signal is symmetric about 0, then it's going to be non-causal. It'll have an equal number of positive and negative samples. And so, in general, we don't like using non-causal filters, but this whole idea of zero phase is really appealing, and so we want to figure out if there's a way that we can have the advantages of a zero phase filter while maintaining causality. And we can almost get there if we have a filter that is finite length. We can convert it to be causal by just adding a delay. So h might look something like this. And for it to be real, or rather for the transform to be real, it would have to be symmetric about there. So if we could just delay this one by 1, 2, 3, 4 samples, we would have exactly what we wanted. So let's call our symmetric filter h sub e of e to the j omega, e for even. And we will package it along with a delay, put our red box around that, and let the red filter, this red box, now be representative of a new filter, h e to the j omega, which is equal to just our zero phase filter, he, times the delay term. And a pure delay has a transform of e to the negative j omega times the delay. Well, if he is a zero phase filter, in other words, it's real. By the way, we call it a zero phase filter even if it has a phase of pi, because it's of the general class of real filters. Then the phase comes out to be just negative omega nd. And that phase is a linear function of omega. It's just negative n times omega. So we call this a linear phase filter, as opposed to the zero phase filter, which was symmetric. And the advantage of a linear phase filter is it is a symmetric filter that has simply been delayed. Now, a key to linear phase filters is that they delay all frequencies by the same amount. To see how this works, let's assume we have a cosine. Cosine omega naught n, and we add a phase to that, phi. We could factor this cosine so that we have cosine omega naught n plus phi over omega naught. Same function. So phi over omega naught is going to be a constant delay for all frequencies, and this is why. If we were to give it a linear phase of minus omega nd, such as we would experience with our linear phase filter, then for phi is equal to negative omega nd, our cosine function becomes cosine omega naught n minus nd. So it's just a regular cosine delayed by nd samples, and it's delayed by that many samples regardless of what the frequency is. On the left, I just threw up a plot there to show that if we were to plot the phase function, you get this nice linear function. So this concept of a linear delay, or a linear filter, linear phase filter rather, is quite useful because we can delay all frequencies by the same amount. So say, for example, we were dealing with a communication system and we had, say, a pulse sequence that indicated ones and zeros. If we sent this over a channel, we would like all frequencies to be delayed by the same amount. If not, if higher frequencies were delayed differently than lower frequencies, then the fact that pulses are made up of different frequencies would cause these pulses to spread out and spread into each other. And it wouldn't take very long before what was received at the far end would be a total mess and uninterpretable. If all frequencies are delayed by the same amount, even if there's some degradation in some frequencies, they're attenuated or something like this, at least the pulse does not spread. And so when it's received at the far end, the pulses remain somewhat distinct from each other and are interpretable. If you're doing work with images, the shape of the image is determined by, of course, the superposition of different frequencies that would be made up of the row scan of the image, for example. And so you'd like a zero phase filter. You wouldn't want an edge to suddenly be blurred as some frequencies are shifted more than others when you do your image filtering. Okay, well, so we've got these wonderful, useful signals. What happens if we don't have linear phase filters? Can we talk about the delay that each frequency experiences if we don't have linear phase filters? And we can. And we use that, the term here is group delay. I'm not exactly sure where the term came from, but this is what it is. Group delay we define as tau, it's a function of omega, is equal to the group delay of h of e to the j omega. And it's defined as the negative derivative of h of e, or the angle, the argument of h of e to the j omega with respect to omega. So let's see how this works if we have just a regular linear phase filter. For a linear phase filter, the angle of the filter is just negative omega nd, And so when we take the negative derivative of that, we get nd is equal to, or tau, the group delay is equal to nd. And so the first thing you might notice is, this is great, our group delay units are simply samples. And the group delay gives us the quantity that we expected to receive based on our previous analysis of what a linear phase filter is doing. So here's an example of the magnitude response of a filter. This one would have several zeros at pi. That's what causes this nice smooth going to zero. Oh, I mistake. This is on a dB scale, no zeros at pi. It only goes down minus 10 dB. So what we have instead are just two poles that you can see as these two hills in the frequency response. If we look at the phase response of this filter, it's approximately linear phase through much of it, but as it gets near the poles, the phase undergoes a radical shift in both cases. So if we were to take the derivative of that phase, we get the group delay. And it shows that where the phase is changing the most rapidly, you have the highest group delay, corresponding to the highest slope here in the phase response. And the group delay is in samples. So we have a group delay of about almost 9 samples right near the pole, and down just below 0 away from the pole. So I have another example that shows this with actual signals and how it affects things. So here we have an input signal that's made up of 3 tone bursts. So it'd be beep, boop, boop, something like that. And if we were to take the Fourier transform of this signal, so this would be the DTFT, and as we'll learn later, we're going to approximate the DTFT using the discrete Fourier transform, but that's how we actually did the calculation. And so what we see is that we have a low frequency, a mid frequency, and a high frequency. And so looking here from 0 to pi, then beyond that we just have the negative frequencies that are our virtual copy of the frequencies. And so the low frequency would correspond to the second tone, the mid frequency to the third, and the high frequency to the first tone. So if we now put this into a filter having a group delay as shown and a magnitude response is shown, so our group delay is shown up here on the top. It shows that we have a group delay of over 200 samples for this little mid-range of frequencies, and very few, around 50 samples for these other frequencies. And then down below we have the magnitude of our frequency response shown here, and we can see we have what looks like a low-pass filter, but it has some ripples. And so we capture the high frequency term in one of these ripples, but lest you think that that means that it gets through, note that this is around minus 100 dB. So it's been attenuated severely. These other signals have been attenuated not so much. This one maybe a few dB, and that one maybe a few dB at most. But you'll notice that they hit at different spots on the group delay curve. And so we can now look at the input versus the output, and we see our input as we saw earlier, but now the lowest frequency signal experienced the highest group delay right about here. And so this low frequency signal is now coming after the mid-frequency signal. And the mid-frequency signal also experienced some group delay, but not nearly as much. Its group delay was right about here, and so it experienced about a 50 sample delay. Finally, the high-frequency signal got knocked down by 100 dB or so, and so it's showing up over here. Not much left of that signal. So there's group delay in theory and in practice. And you can see what group delay can do to a communication system if it can actually change the order in which signals are received. So dealing with group delay and having group delay that is low or even, depending on your particular application, can be very important.